Next talk is Lee White, who I see is appearing on my screen. I hope.
Yeah, can everyone
He's
hear me?
coming. Right? There we go. We're good. Perfect. So yes, Lee is going to be telling us about using atom probe tomography to unravel the age and composition of lunar samples. So give me 1 second while I pull up my stopwatch again. Okay, Lee, when you're ready, take it away.
Okay, well, I'll apologise first off. I am lugging around a cold today, but I'll do my best to soldier through. So yeah, I'm more from the geochronology side of things, and I've somehow been roped into the seedy underbelly of lunar science. So very much technique-driven approaches to questions. So a lot of EBSD, as Anna's just covered very nicely, but also a lot of atom probe. So starting to push things down even smaller spatially to resolve isotopic discrepancies. So just going to give a bit of a summary today, because I imagine a lot of people haven't heard of atom probe. So just going to summarise what it can do and why I think it could be the next frontier for lunar meteorites and return samples. So the big questions have been very nicely laid out by the previous talks. So we care about the age of the solar system, and we care about the age of the moon in particular, because it's such a fantastic reservoir of information for the Earth. So two big takeaways from the age of the moon is that we use it to calibrate crater counting models. So for example, we can work out how old craters are based on the density of craters within that crater broadly. But the moon is pretty much the only planetary body we can actually correlate with known ages. So as well as these crater counting ages, we can take sample ages from known locations, thanks to sample return missions, and actually start to map them together to make sure we're getting the right numbers. And as Anna just summarised, we can also use the moon to more robustly test ideas of bombardment rate and severity in the early solar system. So was there this idea of a late heaven bombardment, a lunar cataclysm about 3.9 billion that has sort of eviscerated the lunar surface and potentially the Earth as well in terms of habitability and sort of sterilising microbes and stuff like that? Or was it more exponential? Was it more of a steady decay as that sort of turbulent early solar system started to calm down and things settled out into the solar system we know today? So we're very lucky that we can directly address many of these questions through sample return, both planned, things like Mars 2020, ongoing in the case of things like OSIRIS-REx, and obviously past missions like Apollo. But we don't have much material, so sample return is a fantastic tool to supplement the meteorite record, but fundamentally we only have grams, if we're lucky, of material. So we really need to maximise our scientific yield from every grain, every section that we look at. And most recently, this has been achieved through correlative microscopy. So rather than just taking a whole rock, crushing it and getting, for example, a TIMS age, so a very precise uranium-lead age, but you have no context for what you've measured, we're now starting to correlate at multiple length scales the whole way through that workflow. So we start off just looking at the whole rock. So as Katie said, mugshots of rocks, kind of give you a starting point of what you're looking at. You cut into it, you get your thin section image, so you can do your backscatter work, your EDS work, your kind of traditional broad chemistry and structure. We come down to the mineral scale. So again, with SEM, higher resolution techniques like EBSD start to come into the fore here, APMA. But now we can even go down smaller to the crystal lattice scale. So something like TEM, we can actually start to pick apart lattice planes within individual mineral grains. So making sure we've got correlative information the whole way through lets us understand what we're seeing at the crystal lattice scale, at the angstrom scale effectively, through those bigger meter to centimeter scale observations. So you really need both to actually understand what you're looking at. And in terms of dating, there are two minerals that are most prevalent. So luckily for me, these have already been summarised quite nicely. But bedelliite, I was planning to spend a lot longer on this slide, but Anna summarised it very well. Bedelliite is a bit of a nightmare, so it's incredibly complex. So this is one of the examples that Anna was talking about in 76535. A massive bedelliite grain. You can see even in the reflected light image that there's a very complex internal structure going on. When we use EBSD, electron backscatter diffraction, we can actually quantify that structure. So in this case, each colour obviously refers to a different orientation of the crystal. But through phase heritage, we can actually stitch all of those orientations back together to work out their precursor phase. So in this case, the reason this bedelliite is so complexly twinned is because it was originally one single cubic zirconia crystal. And then as that's reverted, as it's cooled, it's snapped back to the stable monoclinic phase. So even though it goes through a whole series of tetragonal, cubic, and orthorhombic structures with increasing temperature and pressure, they aren't stable in ambient conditions. So we'll form them, for example, in a melt sheet event or during a shock event, and then it will snap back within a very rapid time frame. I mean, we're talking potentially like hours, depending on how long those temperatures are controlled. In these cases, we're probably talking about millions of years, obviously, as the rock cools slowly. But in synthetic applications, it snaps back almost instantaneously. You can see it happening in real time down a microscope. All that being said, these orientation effects have a massive influence on uranium lead. So depending on which part of the grain you target, whether it's densely twinned or untwinned, that can actually influence your uranium lead measurement. So doing this characterization is critical to understand the age. And same for apatite. Fantastic mineral, widespread in lunar rocks, but a bit of a nightmare when you really look at it structurally. So this fantastic study by Anna back in 2019 looked at a series of shocked Apollo rocks, so looking at the structure of apatite. So in S1, so relatively undeformed samples, you just get nice single orientation apatite, not much going on. But as soon as you start to move up the shock states, you go through recrystallization and plastic deformation until eventually you start to amorphize that lattice. So the mineral can't hold the shock pressure, it just kind of panics and deforms very locally. So you lose those short distance bonds. And again, this seems to influence the effect of lead loss. So how quick lead can get out of that crystal correlates directly with the complexity of the structure. So we need to understand the structure to understand the age. But in both cases, the grains are really complex and really scary. So even EBSD, so this can go down to about 50 nanometer step size, can't quite resolve some of these structures. So we're talking sort of nanometer scale, maybe sub-nanometer variations that we just can't get at. But thanks to Atom Probe, get out of the way, now we can. So this is an example of a 3D Atom Probe dataset. So we get structure and isotopic composition from hundreds of nanometers distance in the mineral. So I'll just play that again. It's quite nice having a video work when you share a slide rather than upload it. So here you're looking at individual atoms of iron, and in the case of the blue, individual sort of clusters of sodium. So we can actually map out grain boundaries. So you can see here, this is a 10 nanometer grain boundary running through a magnetite crystal. And that's something we can only do with Atom Probe at the moment for that 3D resolution. So what is Atom Probe? So fundamentally, sample preparation is the key. So like I say, these samples are 1,000th the width of a human hair, so teeny, teeny, tiny. And to do that, we need to be targeting a feature of interest and then developing that for this analysis. So in this example here, we put down our platinum deposit in our FIB SEM. So we use a focused ion beam attachment to an SEM to extract and prepare these samples. So we protect our surface. So you can imagine your bedelia or your apatite will be under here somewhere. We go in with the micro manipulator. We cut it all around, and then we attach it with a micro manipulator and lift it out. So we've isolated that in 3D and then plucked it out. So it's almost like sort of nanosurgery, microsurgery on rocks, which is really fun. We come out with our lift out and we park it on a silicon post. So these are ready-made sample holders for the Atom Probe. We park it on, we cut off the very end of our lift out. So you can imagine there'd be just this bit here, we snip it off. That leaves us with this kind of morphology, which we then apply the FIB in a circular motion until we mill it down into a fingertip shape. So as you can see here, so this is about less than 100 nanometers at the very tip. So very, very small. So you need to really be targeting your feature of interest to make sure you catch it, because you're only going to run a few hundred nanometers of this sample. Once you've got your sample prepared, we go to the Atom Probe. So you put your fingertip shaped sample in, you load it up, and then using a local electrode, we basically field evaporate atoms and compounds and cations individually to a time of flight detector. So it's also position sensitive, which is where the 3D aspect comes in. So we have our sample held at cryogenic conditions. We apply a laser pulse. That energy transfers up the sample until a couple of atoms get really excited and then fly off to the time of flight detector. We get the 3D aspect from the position sensitive detector. So if it comes from the top of the sample, it'll hit the top of the detector, bottom of the sample, bottom of the detector. And then we also get the Z aspect based on the laser pulse that activated that evaporation. So the first pulse will evaporate the top atom, the last pulse will evaporate the bottom atom. So you have your X, Y, and Z coordinates, and you have the mass, the time of flight mass of that cation. So you can actually put together a 3D reconstruction of isotopic precision. So this is an example data set. It's very much human error when it comes to arranging these things. So the system isn't smart enough to tell you what you're looking at, so you need to have a bit of a handle on the chemistry beforehand. So again, correlative EDS or EPMA is fantastic to have that information to hand. And then you go through and you pick out your individual isotopes, your individual sort of species, and then you can quantify that, as well as selecting what you want to see in that 3D reconstruction. So if you only want to see where your magnesium is, you click the magnesium button, and then it will show you only the 3D distribution of that cation or that compound. So what can Atom Probe do for lunar science? So as we just heard, meteorites and return samples are really complex. So they record a range of ages, a range of structures, a range of class, and we need to be able to pick through that to unravel the true history of those materials. So an example from a meteorite here, this is NWA 3163, so granulitic, Grubric and orthosite breccia. It's been dated before, so we've got model rubidium strontium ages of about 4.3, which seems to be the number of the day. A known impact and granulation event at about 3.3, so that's from argon-argon studies, and then a younger impact at about 1.9, so 2 billion years, again from argon-argon. So known ages. So we're not trying to rewrite the history books of this. We're not trying to change the wheel. We are just trying to date on a very small scale known N members, known entities. So we look at the bedelliote within this sample. So again, a range of class, a range of matrix, but fundamentally they occur with ilmenite, and structurally, as Anna was just showing, they are very complex in these meteorites. So you can see here some are single orientation. So when you look at the pole figure and you start to see these these orthogonally related clusters, that's giving you a hint of phase heritage. So that idea that there was one cube, and that cube is broken down 3 orientations on each of the cube faces, which would be 90 degrees apart. So evidence of high temperature or pressure examples. In this case, is in a felspar melt, so we're probably looking at high temperature effects, or again high pressure, depending on sort of the history of that grain, and you can pick out these clusters. So, but you can see even in this 1 micron sized grain, tiny bedelliote, there's a lot of variation. If you were taking a thin spot, something like a TIMS extraction, what would you be dating here? Because there's so much going on. And Atom Probe lets us see through that. So in this example grain, about 5 microns long, looks nice in backscatter imaging, but as soon as you go in with the EBSD, you can see that there's amorphous domains, there's different orientations, different levels of band contrast, and that's what we can pick out here. So the core of the grain is polysynthetically twinned, so you can see here this kind of repeating structure, and then we have a single orientation sort of rim overprinting it. So we know the sample went through multiple impact events, went in with the Atom Probe because we have the spatial resolution to do that, and we targeted the twinned core of the grain and the overprinting rim, and that allowed us to actually get chemical and isotopic composition from those domains alone, rather than homogenizing them into a single measurement. We couldn't measure uranium, but we did get thorium. So we got a nice peak of thorium-232, double charged at 116. And again, we got lead, obviously 208, double charged at 104. And then that allowed us to calculate the thorium lead age for these samples. So no obvious variation within them. So again, we're looking at sort of 400 micron to, I mean, this is a massive data set, but boring, unfortunately. But we got really robust thorium lead age as a result of all those counts. And you can see here the Atom Probe, the twin domain, actually give us an age concurrent with the modeled rubidium strontium age, as well as a separate SIMS age we did on a twinned grain within the sample. So we can be quite confident that this core is recording the crystallization age of that sample. And then the rim domain actually gives us a thorium lead age of about 2 billion. So again, that's starting to match up with that youngest argon-argon sample. So we've got sort of 2 billion years of history recorded within a 5 micron bedelliote grain. And Atom Probe's the only way we can really start to pull that apart. There is another example from the Apollo record, which Anna published last year. I won't go into that today, just because of time. But if anyone's interested, I'd highly recommend looking at this paper, because it's a fantastic example going from Atom Probe to crater scale and really starting to pull apart the age of Trinitatis impact basin using these new techniques. Skip. As well as age, we're also pulling apart volatile compositions now. So measuring water, measuring chlorine and fluorine. An example last year from Darling et al. Actually got accurate chlorine isotope measurements from a Martian apatite. So we can actually visualize the distribution, for example here, of iron to pick out grain boundaries. That vaguely matches with chlorine when you start to look at higher resolution sort of maps. But then when you actually look at it, a concatenated, so a combined data set from multiple Martian tips, give us bang on the chlorine isotope ratio for basaltic shergottites. So that's the first ever example of chlorine isotope measurement working with Atom Probe. Space weathering on the moon has been imaged now with Atom Probe. So, how deep, we're talking about hundreds of nanometers of implantation from solar winds in a lunar regolith. We can actually start to map that out with Atom Probe, in a study by Jenica Greer et al. And then just hot off the press, we've actually now started to measure water accurately using cryogenic preparation through that sort of polishing stage. So in the case of DR5, which is a known basaltic reference, there's about 0.5% water. When we pull apart all of these very complex hydrated peaks, so you've got silicon and magnesium and iron, they take on the hydrogen. When you start to break those all apart and then deconvolute those peaks, we actually now starting to get the right amount of water within that standard. So we can now actually measure water and chlorine as well as age, so using Atom Probe. So very much been a team effort over a very long period of time. Lots of people to thank here. I'll just shut this up. And that's where I'll leave it. So Atom Probe is very much the future, I think, for sample return, maximizing your scientific yield, but you need that bulk understanding to really understand what you're seeing on this angstrom scale, because otherwise you're missing the wood for the trees. So thank you.
Thank you, Lee. I'm trying to work out whether I'm a part of the seedy underbelly of lunar impact chronology.